Okay, we start new section, section 3, which is about linear regression. Linear regression is probably the most popular and most widely used technique to analyze relationship between variables. Regression provides us a conceptual approach to investigate those relationships and understand how one or more factors affect an outcome of interest. This relationship between variables, or between inputs and the output variable, is expressed in the form of an equation which we call a model. And this equation connects the response, or dependent variable, and one or more explanatory variables, or predictor variables. So that's the first piece of the terminology. So we have the model, um, and the model takes the dependent variables, or the inputs, and produces an output. And so the model is just some equation that takes some numbers and produces an output. And the input and outputs comes under different names. So typical name for the input variables will be um, explanatory variable, predictor, or independent variable. And the output variable is typically called dependent variable, or response, another name for it. So those are equivalent. So we can say output, dependent variable, response is the same thing, or we can say input, explanatory variable, predictor, or independent variable. It means the same thing. And model is just an equation that links the inputs and outputs together. So let's look at the first example. Henrietta Leavitt, who was a astronomer in the Harvard Observatory, and she made this discovery in 1912. She realized that there is a relationship between period of oscillation of pulsating stars and their luminosity. So pulsating stars is a star that changes its luminosity in time, and it basically become brighter, 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 then goes dimmer, 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 then brighter, 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 dimmer, 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 dimmer. And what she did, she took the stars, then she actually then called standard candles. Standard candles are the stars for which we know the true luminosity, so their true brightness. And then she measured the period of oscillation. And what she realized, that there is a relationship between the period of oscillations of those pulsating stars and their true brightness. When she plotted the data on the scatter plot, she actually realized that the relationship is linear, or at least linear on the logarithmic scale. If we put the oscillation on the logarithmic scale and we put the true luminosity on the logarithmic scale, then what we have is the larger the oscillation period, the brighter the star is. And actually, if you draw the line, then you actually can see that the relationship is pretty good. Now, why is that important? Why do we, this relationship is important? Well, this relationship allows us to calculate distances to faraway galaxies. And the way we do it is, so you look at an object in a faraway galaxy, and you look at the pulsating star in a faraway galaxy. And so let's describe the process of, so calculate late distance. Okay, the way you do it is you look at the object in the faraway galaxy, and you calculate the oscillation period is calculated first. And then let's say on the logarithmic scale, the oscillation period is 35 days. So it's somewhere here. Okay. So once you know the oscillation period, which is roughly, here, 35 days, you actually can predict what is the true luminosity will be of that object. Okay, so you say, okay, so let's say it's equal to 35. Then true luminosity, or brightness, of this object is roughly 12. Okay, and once you know the true brightness of the object, what you can do, you can compare it with the how bright it appears from the Earth. So compare to how bright it appears from Earth. And there is what is called the inverse square root law, meaning that the brightness of the object changes as 1 over square root of the distance between the observer and the object. So if you know the difference in the brightnesses, how it appears on the Earth, and what is the true brightness of the object, you actually can calculate the distance. Then you can calculate the distance. So it basically allowed us to calculate distance between the Earth and faraway galaxies for which we cannot calculate distances in any other way. That was the only way for us to do it. And Henrietta Leavitt was actually not the person who reported the results. Somebody else reported it. But her job was to take images that were generated by a telescope and just record data. And so we didn't have any automated way to analyze images those days. It was a human who would sit down, look at an image, and look at the luminosity or the brightness of the object, and then we'll basically record this data. And at some point, Henrietta Leavitt just plotted it and realized there is a linear relationship between the luminosity and the oscillations. So, and in artificial intelligence, the criteria for evaluating prediction rule is simple. How big is the error that the rule makes on average? And in the case of Henrietta Leavitt, the average error was 0.28. And now you say, okay, so she had this linear model. So the linear model basically says that it says that the luminosity or the brightness is just some number alpha plus beta times the period. Okay, so it's just equation of the line. So what we hear on the right hand side, equation of the line, in the high school math, you're more familiar with y equal to a plus bx equation, right? So x is the input variable, a and b are the parameters of the line, y is the output. So we just call this one y, this is our a, this is b, and this is our x, converting into the language of high school math. Anyhow, so the question is, how do we find the line that predicts the data the best? And the way we do it is by looking at the errors generated by this line. And so what you see this line on the left-hand side, so is when compared to the line on the right-hand side, actually the left-hand side line is better because it generates less errors. So error is just the distance between the point, observed point, and the prediction made by the line. So prediction made by the line, if you look at the distance between the point and the line, so that's called an error. And then you calculate average, and in Henrietta Leavitt's case is 0.28. And you can say, okay, maybe it's not a good model. Maybe you can find a different model. And different model basically, okay, maybe you can try a different line here. And if you calculate errors for this line, they become larger. So essentially, Henrietta Leavitt model was the best. Best means you cannot find a different line that leads to a smaller average error. All right, and essentially you saw the process of making the prediction. So we tried to predict the luminosity of a star from the period, and the period is easy to calculate, right? So you just observe the star and you see the difference between the peak brightnesses, and that gives you the period. And so that's that, and we generate prediction by basically looking at the point on the model on our line. And so the same way prediction is done by many businesses in many different contexts. And so examples are, how much will my house sell? So this is example of Zillow. So the whole business model of Zillow was built on ability to predict price for each of the houses. And the way they do it, they use very similar model. So the inputs will be not just it will be the square footage of the house, location of the house, the amount of land, and different features of the house. And given all these attributes of the inputs, they try to predict the price. Will the Chicago Cubs win the World Series? So you can try to build a predictive model based on the historical performance. Will the person like the movie, a Netflix example? And so that's one way to use those predictive models. So we want to predict actually something. Another way is to actually do the explanation or understanding of the relationships. For example, we want to know what is the impact of a degree, of master's degree, on your income. So we don't want to predict specifically what your income is going to be given a degree, but we want to understand this relationship. So how much your income going to go up. So the relative change in the income given the degree. Or how does the returns on Google relate to the market? So how strongly the Google and market are related. Again, we're not interested in predicting Google prices. It's actually quite silly exercise, at least using the simple linear models. But simple linear models can help us understand the relationship between Google and the market. And the fact that most of the fund managers use linear models, it's called CAP-M model, which we'll talk a little bit later in this section. All right, so let's talk about models, their parameters, and how we estimate those parameters. So we're gonna use probability to talk about uncertainty, the same thing we did in the previous sections, and we're gonna build models by defining the output variable. We're gonna call it y, and we will treat it as a random variable, and then we construct a regression model from the historical data, and we're gonna use input characteristics x as the input to this model. And then we will relate x and y and the parameters or the of the equation. So so if we're going to have, for example, y equal alpha plus beta x, so this number alpha and beta will be called parameters of the model, and the whole equation is just called the model. So it's a mathematical model of the relationship between x and y. It's an abstraction. It's not necessarily things change in a linear way. It's just happens to be the case that this linear relationship is a good enough way to describe this relationship. And once we build the model, and once we estimate the parameters, so the parameters are calculated. And actually in statistics, instead of saying parameters are calculated, statisticians use word estimated. Parameters are estimated. To highlight the fact that this is not true value of the parameters, because they come from, we do it based on the data, calculated from data. So again, we have some uncertainty about the parameters, because if you imagine Henrietta Leavitt's experiment, she did it for 25 pulsating stars. If she goes and takes another 25 pulsating stars and do the same linear model, same linear relationship between the different set of the stars, actually the line might look slightly different. So if you go from one data set to another data set, your parameters of the line might change. So the slope of the line might change, for example. So that's why we don't say we calculate, we say we estimate it, highlighting the fact that we're not certain about those parameters. So once we have the model, then we can start doing the prediction, we can start evaluating the risk, making decisions. So there's a whole bunch of things we can do based on those models. All right, so let's look at a specific example, predicting the housing prices. The problem is to predict the price of a house based on the observed characteristics. So this is essentially a Zillow problem. And we will look at the property sales data, historical data, where we know the price. So we know for what price the house was sold. There was a transaction associated with that house. And then we take some observed characteristics about the house. And then we build a decision model that predicts the price for the house that hasn't been sold for a while. So you take a house that has been sold last time 20 years ago, the price that the house was sold 20 years ago is irrelevant now. So we want to understand if we had to sell a house today, what price we're going to get. So we're going to look at the more recent sales, and we're going to build our model based on those more recent sales, and we're going to predict the price for our house. Essentially, again, that's the Zillow business model. They build those predictive models, that they're bread and butter, and they actually use R, the same tool that we use in this class. And this estimate, what they call, is basically the y variable that they try to predict. So this is predicted price. Okay, and the way their model looks like, right? So they have some model, and they take inputs, and the inputs is the square footage number of bedrooms, number of baths, the size of the lot of the house. So basically all the characteristics of the house that you can get from the county website. The way they do it, they go through the county because every house has to have a record in the county database. So they take this records from the county database, and then the price is the outcome. Again, every sales of a house has to be reported to the county, and county reports the sales transactions. So they take those sales transactions and then they relate this characteristics of the house and the price of the house. And so they have those huge databases, right? It's terabytes of data. And Zillow, so we're going to talk about linear models in this section. So Zillow employs a little bit more sophisticated model, which is called decision trees or random forest. And they actually use multiple models at the same time. So different models have different advantages and disadvantages, different predictive models. And what they do, they basically average out different models. And the prediction that you see is the result of the multiple predictions averaged out across multiple models. And there was one of the Kegel competitions. So Kegel is a platform that allows companies to sponsor a competition. And in a competition, the company will publish a data set and they say, we want to you to predict whether the property is, in the case of Zillow, whether it's waterfront property or not waterfront property, and based on the characteristics of the house and price of the house. So the Zillow price Kegel competition was waterfront or not, and they give you different characteristics of the house and they ask you to predict. And the way it works, they give you some what is called training data sets, so some historically observed transactions on the houses, so you know the sales data and you know the characteristics of the house and you know whether it's waterfront property or not. And then they take another smaller data set and they ask you to predict whether it's waterfront property or not. And in this small data set, they actually don't tell you whether it's waterfront property or not. So you do the predictions and you send them what your predictions are, and then they compare your predictions to the actual characteristics for each of the houses. And then they basically give you a score. The score is the difference between your prediction and the true ones. And the person who predict the most accurately will win the competition. Anyhow, so the characteristics that Zillow uses, so as I said, the size of the house, location, zip code where the house has garage or parking. There are multiple attributes of the house that Zillow uses. We're gonna do a simpler version of the Zillow problem, and we're gonna look at predicting the housing prices just purely based on the square footage. So again, so let's go back to the terminology in the context of housing prices. So we would like to predict the output, which is the housing price, and we call it dependent variable or the output. And the variable that we're going to use, our explanatory variable or input, is the size of the house. So this is thousands of square feet, just two variables, right? So we want to build a model y equal to alpha plus beta x, and here y is the price and x is the square footage of the house. And we're going to use this linear relationship. So this linear relationship has two parameters, alpha and beta. Sometimes you'll see alpha and beta. Sometimes you will see, instead of alpha and beta, we're going to use beta 0 plus beta 1 x. It's the same thing. It doesn't matter how you name the variables. The essence is the same, whether you call it alpha and beta or beta 0, beta 1. This is probably a more standard way to name the variables in the statistics. And in the econometrics, when they talk about kappa models, so that's in the econometrics, that's probably a more popular way to name the variables. But either way, it doesn't change anything about the problem. So let's look at the data. We're going to look at the sales data from one of the counties in New York. And so on the x-axis, we have the living area measured in square foot. So we have houses up to 5,000 square foot here. And here we have a price measured in $1,000. So we have, the most expensive house here is slightly under $800,000. This is data from 10 years ago where house prices were much lower than they are today. So, and again, we see that looks like the relationship, the linear relationship might be a good enough model for us to do the prediction. Of course, there are outliers. So you see, for example, this house, so this one, or this one. So look at this one. So this house is very small. So this is small but expensive. And this one is large but cheap. Okay, so it looks like we have a couple of outliers, and there are multiple reasons. So maybe the large and cheap house, maybe because the house is in bad condition, and there are a lot of work needs to be done. But that's something we don't really know because our data set only has the living area, so it doesn't tell us anything about the condition. So we basically have to say, okay, based on the living area, that should be the price of the house. So the price of the house based on the living area should be around 300K, but the house actually sold for around 70K. So it's a huge discrepancy. And now we have this small but expensive house. Again, this might be a boat house or some waterfront property in a very expensive neighborhood, or it can be a big lot of the land and only small houses built, and person sells it expecting that an actual bigger house will build there. So we don't really know. We don't have any explanation to why we see those outliers. The only thing we can say that they are outliers in this data set. Okay, so let's build the model. So this is our model. We're gonna say that price is just linearly related to the square footage of the house. And again, since if you look at the data that the points do not perfectly lie in the line, so they actually deviate from this line, we say that the price is the point on the line plus some error. Okay, and that's how we write the statistical model. So this is called deterministic part, and this is stochastic part of the model, or random part. Random means we don't have any explanation for why the prices actually deviate from those points on the line. We just say, okay, this is just some error that we're going to add to the model, which is a random component. Okay, and for the linear models, we assume that this error follows normal distribution centered at 0 with some standard deviation sigma. And the error term models the fact that not all prices will lie again on the line. And so once we fit the model into the data, so once we try to find those beta 0 and beta 1, we find out the beta 1 is 0.11, which basically means, let's look at the units. So price is measured in dollars, and the square footage is measured in square footage, right? So the units of beta 1, so beta 1 has to take something measured in square feet and convert it into dollars. So units for beta 1 is dollars per square foot, right? So if you multiply this by square foot, you get the dollars. Okay, so which means, in other words, beta 1 measured how much price changes as a result of changing the size of the house. So beta 1 measures how much price changes, and price is measured in dollars, if square footage of the house goes up by 1. So if your house is to have an additional 1 square foot of the area, how many additional dollars you expect? And it happens to be 0.11. And remember, it measured in the thousands of dollars, so it's basically 110 dollars per square feet. Okay, so on average, the house in the Saratoga County in New York is sold at the price $110 per square feet. That's what the model tells us. All right, now let's look at the prediction. So we estimated that beta 1 was 0.11, and we estimated that beta 2 was 13.44. Sorry, this is beta 0 is 13.44. And now we can do the prediction. So let's say you try to sell your house, and your house has 2,200 square feet, and you try to predict the price of your house. So try to say, what should I ask? So what you do basically, you plug in this x, your input to the equation that relates the square footage of the house and the price of the house, and you get 262. So 262,000 is the price that you should expect somebody will be willing to pay for your house. Now let's look at another parameter of this model is beta 0, which is called intercept also, and this is 13.44. And let's look at the units. So units of beta 0. Beta 0 is measured in dollars, right? Because you basically have dollars on the left-hand side. You have dollars on the left-hand side, and here you have to have dollars plus something, right? So here you have dollars plus dollars. So it's measured in dollars. And if you think about the way you interpret this, the way you interpret is you basically say y equals to beta 0 if x equals to 0. So let me say it using the human words. If the area of the house is 0, meaning that there is no house on the property, then the price of this property will be equal to beta 0. Or in other words, beta 0 is price of the land that you have on your property. So this is just nothing but price of the land. So in this case, we actually have very nice interpretation of the parameters of the model. Beta 0 gives us the price of the land, and beta 1 tells us the price of the house per square foot. And now, so we showed an example of doing the prediction. So we tried to predict the price of the house, and we also did the interpretation. So we can learn something from the model. We learned that $13.44 thousand is the average price of a land in the Saratoga County. And we also learned that an average price per square foot of a house on that property is $110. All right, so we do prediction and we do interpretation in this housing example. And the way you can do it in R, so that's the full script. So read.csv reads the data. And I'm going to put example of this into the one of the source codes for the class. So we have, we read the data set, and then we divide price by thousand. So we convert from dollars to thousands of dollars. Then we plot the relationship. This is the relationship that you've seen in the plot. So this is the dots. And we build the model. So this LM function builds the linear model. So LM function basically finds the parameters. So this LM function estimates beta 0 and beta 1. It does calculate what is the optimal line, and the way it calculates the optimal line by looking at the line that leads to the smallest average error. And then you can use the coef function to look at the coefficient. So basically it will just print this beta 0 and beta 1 on the screen. And then this AB line function will just print the plot of this line associated with this model. And another function that you might want to know, so that's pretty much the whole process of building linear model in R. So again, this is just reading the data, preparing the data. This is exploratory data analysis, so that it doesn't even relate to building the model. So actually building the model happens in one line here with this LM function. And let's look at the syntax of this function. So first argument is what is called formula. So let me erase this one. So this part is called the formula. And the way you specify formula, you say what is your y variable, and then you say tilde. So, and after the tilde, specify what is your x variable, and in this case, living area. So basically y tilde x, and in our case y is the price, and input variable x is the living area, and then I specify which data set to use to build the model, and that's pretty much it. So, and then you can analyze your model by looking at the coefficients, and then you can plot the results of this model on the screen. So let's look like how this is done in R. So I have the same code that you've seen on the slide here in R. First we read the data. So it's saratoghouses.csv. We use read.csv command for that. Let's look at the data. We're going to use the head command just to look at the first 6 rows of the data set. So this is the columns that we have. We have price, lot size, age, land value, living area, then number of bedrooms, fireplaces, etc. So we're going to focus on those 2 columns. We're going to use Y for the price. This is going to be our output, and input going to be the living area. So this is our X. So next thing we do, we convert prices from dollars to thousands of dollars. So we take the price column of the data set and we just assign the new value to it, which is itself divided by 1000. All right. Now we're going to plot this relationship as the same plot you've seen, slightly different graphics. So if we want to get the same looking graphic as you see on the slide, we're going to change the marker. So 16, and I'm going to say color is light blue. All right. I think that's how it looked, but I don't remember. Anyhow, so that's the data set, okay? And then we're gonna call this lm command. So we just say we're gonna regress living area to price using the data house, and the coefficient of the model will just print the coefficients. So interset, which is a beta 0, 13.4, and beta 1, which is coefficient associated with the living area input, 0.11. And AB line command will add this line to the plot. So let me make it like this so you can see it slightly better. So it's the same thing you've seen on the slide before, and that's pretty much it. So we are done building the model, and this is the coefficients of the model.